Hi guys, in my previous concept I discussed about if we keep a bar magnet in the presence of an external magnetic field, or this bar magnet also we call as a magnetic dipole. Magnetic dipole or a bar magnet. If you keep a bar magnet in an external magnetic field, so because of the two opposite forces which acts on the poles of the magnet, that causes a torque. So we derived expression for torque, tau equal to mb sin theta So this we write in the vector form tau bar equal to m bar cross b bar. So this is the expression for torque. Now today's class I would like to discuss a new concept. Suppose if we have magnetic field, so let it be this is the direction of magnetic field, it is moving along positive x-axis direction. Let us consider that as positive x-axis direction. So in this uniform magnetic field, if we place a bar magnet, so I would like to place a bar magnet So I draw a small bar magnet. So is placed in an uniform magnetic field. Let it be a bar magnet or a magnetic dipole. So don't be confused. I always use bar magnet or magnetic dipole. They both are equivalent. They both are same. So because of external magnetic field, this is the magnetic field direction. And if it is north pole and this is south pole, two opposite forces will act. The two opposite forces cause couple. So this is the force which acts along in this direction, force F equal to Qm times B, and another force also acts in the another pole which is same in magnitude. So that I can write that this force F equal to Qm times B. So here Qm called as magnetic pole strength. So Qm is magnetic pole strength. Now we know that one. So this magnetic field and forces that both cause torque. Torque tau equal to mb sin theta. So because of torque, the magnetic dipole starts to rotate in the magnetic field. It causes to rotation. Suppose if I do an external work, suppose if the dipole is rotated against the action of its torque, if I am doing work, so what is my work? So my work is to rotate the dipole against the torque, action of torque. So to rotate the dipole against the action of its torque. Action of its torque. It means if the dipole is rotating clockwise direction, suppose if I am doing work, so that work is to counter torque. So I am doing work against the torque. So how can I write the expression for work what I do? So we know the work formula, work equal to product of force times perpendicular distance. Not perpendicular distance, just force times distance. So here force in this particular tau is a force, and distance equal to theta because it's aligned with an angle theta or angle distance. So if you take this as work, so I would like to write the small work equal to tau times small d theta. Now the expression for work at here dw equal to tau times d theta. So we know the tau formula, tau equal to mb sine theta, torque expression, times d theta. So this is the small amount of work which I am doing against the torque. Suppose take a case. The case is if the dipole is rotated. The dipole is rotated from initial angle theta 1 to final angle theta 2, some angle theta 1 to theta 2. Now initially if you take a certain angle as theta 1 in this magnetic field, if this is initial angle theta 1, now if I am rotating dipole to another angle, so let it be take the same figure. If you take that another angle in the dipole, so if that dipole is rotated to another angle, so if this is the orientation of the dipole, now it is making an angle with the horizontal. Let here take as theta 2. Now there is change in angle. Now to rotate that dipole against its torque, how much work I do? So to calculate the total work, so total work W equal to integral dW. I need to do the integration to get the total. If you do the integration, integral mb sine theta times d theta. But here the limits are initial limits theta 1 to final limits theta 2. To get the expression for total work, W equal to mb is non-integrable term. You can take it out of integration. W equal to mb of, I can write one more step here, integral theta 1 to theta 2 sine theta d theta. So W equal to mb, integral sine theta, it goes to minus cos theta times theta 1 to theta 2. And if you can substitute the limits, and it will be ended up like this: W equal to mb of minus cos theta 2 minus times plus cos theta 1. And if you rewrite, it becomes W equal to mb of cos theta 1 minus cos theta 2. So this is the expression for work to rotate a dipole at an angle theta 1 to theta 2 in the magnetic field. The good thing is that here, now this work done, whatever we do work, so that work will be stored as the potential energy U of the dipole. So we know that the work done. So how much I am doing work there? The work done is stored. The work done is stored in the form of potential energy. We represent that potential energy with a letter U. So now I can write that this is the work done by me Don't forget that. So this is the work done by me. So I did that much work to rotate the dipole against its torque. According to conservation of energy, work is nothing but energy. Whatever work we do, that transforms in the form of energy. So here that work gets transformed in the form of potential energy. Therefore we can write the potential energy of dipole. The potential energy of dipole equal to, we can write that U equal to mb of cos theta 1 minus cos theta 2. It means here we got one more expression. If you place a magnetic dipole in a magnetic field, so the magnetic dipole is having energy, potential energy. Suppose we take a case at here, if magnetic moment M is perpendicular to B, so here theta is angle measure, we do like that. If magnetic moment is perpendicular to B, so the potential energy of the dipole at an angle. So in that case, if I take theta 1 equal to 90 degree and theta 2 equal to any angle theta. So if I draw that in figure to make you understand, so if it is dipole magnetic field, so this is magnetic field. So in this magnetic field, if I keep a magnetic dipole, so initially that magnetic dipole is perpendicular to, magnetic moment is perpendicular to magnetic field direction. So this is the initial case. Initially this is the position. So the magnetic moment is exactly perpendicular to magnetic field direction. Let me highlight. This is my magnet or magnetic dipole or bar magnet. So initial angle theta 1 equal to 90 degree. So here theta 1 equal to 90 degree. Suppose I am rotating this at here some another any random angle. So if I am rotated that to initially theta 1 to some another random angle in the magnetic field, now this angle equal to some theta. The magnetic moment is making an angle with the magnetic field that equal to theta. So you don't forget that theta is angle between magnetic moment and magnetic field. So initially it is 90 degree. And if we rotate it at an angle of theta, now the above expression will simplify as the potential energy U equal to, so I can take this as potential energy U equal to mb of cos theta 1. So cos theta 1 value equal to 90 degree minus cos theta 2. Cos theta 2 in the place cos theta 2, we have to substitute theta. So cos 90 value goes to 0. Therefore potential energy U equal to minus mb cos theta in this case. So this is easy to remember and an easy condition also. Let you take the condition is like that. If that magnetic dipole initially is perpendicular to the magnetic field, it means magnetic moment vector and magnetic field vector are perpendicular. Now if we rotate the dipole at an angle theta, so whatever the work we do, that work stores in the form of potential energy. The expression for that U equal to minus mb cos theta. So you can shrink this expression minus times m bar dot b bar. It's a dot product of two vectors. It becomes u equal to minus mb sin theta. Sorry, minus m bar dot b bar. What about the minus sign tells about it here? Think about that. What is the minus sign tells about that? And after, if you can get any idea of that, let us check your idea during the examinations. Suppose if you take a case, the case is when theta equal to 0 degree. It means initially you are making 90-degree angle, initial angle of the magnetic dipole magnetic field. Now from 90 degrees to you are rotating to 0 degree. So it means that the magnetic dipole is parallel to the magnetic field. So theta equal to 0, the potential energy. So the U equal to minus mb cos 0 degree, which value goes to minus m times b. The potential energy value here in this case equal to minus mb. Suppose you rotated from 90 to 0 degrees, so that you can mention. Rotated 90 degrees to 0 degree. Now second case, when theta equal to 90 degree, means you do not rotate. Not rotated. Initially it itself is 90 degree. And now you do not rotate. By the time the potential energy U equal to minus mb cos 90 degree. So cos 90 degree value equal to 0. So the potential energy in this case equal to 0 if theta equal to 90 degree. So what happens if you rotate from when theta equal to 180 degree? It means you rotated from 90 degree to 180 degree. So in that case the potential energy U equal to minus mb cos of 180 degree. Cos 180 degree value equal to negative 1, so its value becomes positive. So the potential energy of an magnetic dipole in a uniform magnetic field in this case equal to positive, and which is maximum. So this is case also you can take for maximum, and this case you take for the potential energy minimum. Sorry, not this case, above case. Negative is less than that. So here potential energy minimum case. So that's the potential energy of a dipole is maximum. When it is maximum, very important point, take as a note, potential energy of a magnetic dipole. Dipole is maximum. Maximum when magnetic moment vector is anti-parallel to magnetic field vector. So I hope you know both the direction. Magnetic moment vector is represents in the bar magnet from south to north pole, and it is anti-parallel to magnetic field vector. So if I draw a diagram at here, suppose this is magnetic field direction. Magnetic field direction, this is a B bar direction. Suppose if I have a bar magnet, so that bar magnet having magnetic moment vector along in this direction. So this is south pole of a bar magnet. Suppose this is south pole of a bar magnet and this is north pole of a bar magnet. I do not draw bar magnet, but imaginary you can say. So this yellow line itself is a bar magnet. Okay, now here the magnetic field vector and magnetic moment vector. So magnetic moment vector I represented here, this is a M bar. Magnetic moment vector is always from south to north of a bar magnet. So here the yellow line itself is a magnetic dipole. I do not make a boundaries and all, but you just get the common sense. So the angle between them, magnetic moment vector and magnetic field vector, in this case equal to 180 degree. So here magnetic moment vector is anti-parallel, is an anti-parallel to magnetic field vector. In this case the potential energy of magnetic dipole is maximum. And when it will be minimum? So when the dipole is exactly perpendicular to. So this case we call as the magnetic dipole is in unstable equilibrium. So in this case the magnetic dipole is in unstable equilibrium case, equilibrium state. So this is all about the concept of potential energy of a magnetic dipole in an external magnetic field. So you remember that formula? To derive that we need to get the expression for torque, and after here the key point is that we need to do work. So whatever work we do, that work is stored in the form of potential energy. Keep practice the derivation.